So much like in the warm-up, when we added and subtracted polynomials, we are looking for like terms. We're going to do the exact same thing. We're adding and subtracting radical expressions. So I'm just going to have a square root of something. And when we do this, we want to look for radical expressions to be like radicals or like terms. What this means is they have to have the same root. For instance, the square root of 2 is the same as square root of 2. Or the square root of 5 is the square root of 5. Just like we see in these examples here. Now, square root of 2 and the square root of 5 are not radicals because they're different numbers on the inside. I'm not worried about the numbers on the outside as we see in the first example, simply the numbers on the inside of the radicand. So let's compare these two polynomials. If I'm going to add like terms of a polynomial, these are both monomials, so 4x plus 2x equals 6x. I did not touch my x's, I simply added the coefficients. Same thing if I have 9y minus 7y. I'm not going to touch my variable, I'm only going to subtract the coefficients. So 9 minus 7 is 2y. I'm doing mostly the same thing when I'm dealing with radicals. So I notice that square root of 5 and the square root of 5 is the same, so I'm going to keep that. That is my like term, and then I add the numbers on the outside. So 4 plus 2 equals 6. Same thing as I'm working through this one. Square root of 3 is the same as square root of 3, so I keep it, and then I simply subtract 9 minus 7, which would be 2 on the square root of 3. So as I'm solving each of these examples, the first thing I want to ask myself are the radicands the same? So square root of 5, square root of 5. Yes, it is. So I can simply add the numbers on the outside. 2 plus 7 is 9. Are my radicands in number 2 the same? Yes. Square root of 7, square root of 7. I cannot forget, though, that there's technically a 1 on the outside of the radical sign. So 9 minus 1 will give me 8 on the square root of 7. Now, even if there are more than just 2 parts or 2 terms, then I have to check each one. Square root of 3, square root of 3, square root of 3. They're all the same, so all I have to do is add or subtract numbers on the outside. And don't forget that there's a 1. So 5 minus 2 is 3, and 3 plus 1 is 4. So my final answer will be 4 on the square root of 3. When I get to number 4, I notice there's a little bit of a difference. I've got the square root of 6 and the square root of 6, they're the same. So I'm definitely going to add those numbers on the outside. 10 plus 4 is 14 on the square root of 6. But if you notice, I have a whole different term here with the square root of 2. I'm going to leave that in the problem. I can't magically get rid of it, but I'm just going to bring it down. So my simplified version is 14 on the square root of 6 minus 5 on the square root of 2. This is very similar to if I had a problem like 5x plus 3x minus 8. I can only combine the like terms, so the 5x and the 3x would give me 8x, and I have nothing to combine with the constant, therefore it would stay the same. Well, what happens if our radicals are not the same? Sometimes we can simplify in order to make them the same. So I always want to check if they're not the same, can I simplify in order to make them the same? So I noticed that square root of 2 and square root of 8 are definitely not the same. So just like in our warm-up, how we simplified, I'm going to find the factors of 8. So that gives me 4 and 2, and the factors of 4 are 2 and 2. When I look here, I have a pair of 2's with a 2 left over. I'm going to keep my 3 on the square root of 2 that I have, and I'm going to add it to my new simplified version, which would be 2 on the square root of 2. At this point, I can see that I have like radicals. So 3 plus 2 is 5, and that answer will be on the square root of 2. Now, as we look at the next one, 5 on the square root of 3 minus the square root of 12, and clearly 3 and 12 are not the same. So I'm going to break down 12 to be 2 and 6. 6 can break down to be 2 and 3. Again, you can find any factors that will multiply to give you 12. You don't have to pick 2 and 6. You could use 3 and 4. And as long as you're getting them down to the prime factors, your answers will be the same. So I have a pair of 2's. So I'm going to rewrite 5 on the square root of 3 because it is in simplest form. The only factors of 3 are 3 and 1. It's a prime number. And then I'm going to keep my subtraction. Now I have 2 on the square root of 3. And now my radicals match. Therefore, 5 minus 2 is 3. So 3 on the square root of 3. We look at our two examples. Well, 2 and 18 are not the same. So I'm going to simplify 18. Gives me 9 and 2. Factors of 9, 3 and 3. So if I rewrite my problem, I now have the square root of 2 plus 3 on the square root of 2. Then my 2 is left over. At this point, I can combine my like terms. Remember, there's a 1 on the outside, so 1 plus 3 gives me 4 on the square root of 3. So look at number 6. I have 3 and 27, clearly not the same things. So we'll break down 27 to be 9 times 3. Break down 9 to be 3 and 3. I have a 3 left over. So over here, I'm going to keep my 5 on the square root of 3, and I'm going to change the square root of 27 into being 3 on the square root of 3. At this point, I have the same radicals, so 5 minus 3 is 2. So my answer is 2 on the square root of 3. Now, if I add variables into the problem, it gets a step harder, but it's the exact same concept. All you're doing is combining like terms. So if I look for 5 on the square root of 3x minus 2 on the square root of 3x, I can see that those terms are alike. Square root of 3x, square root of 3x. So all I want to do is do 5 minus 2, which is 3, and then keep my radical of 3x. As I move down to the next example, we have 2 on the square root of 3a to the third, and plus 5a on the square root of 3a. Well, these are clearly not the same thing because they have different exponents. Just like in the polynomials when we started, they have to have the same variable and the same exponent. So I'm going to break this down. 3 is as simple as it gets. It's just 3 and 1, so it'll stay square root of 3. And I have a to the third. So remember, I'm going to take 3 and divide it by 2. That gives me 1.5. What that tells me, on the outside I have 2 and an a. There's a pair of a's. And on the inside, I leave my 3 and I have an a left over. Now I just want to compare to see if it matches. It does. Remember, even when I'm adding like terms on the outside, they still have to be the same. So 2a plus 5a will work to be 7a. And that's going to be on the square root of 3a as a final answer. So as we look at our examples, we have 7y and 7y. Those are the same. So I just want to add the outside. 2 plus 3 is 5. So 5 on the square root of 7y. Now as I look at number 8, I notice that they're not the same. So I am going to try and make them the same. The first thing to do, though, is to simplify 20, which would be 4 and 5. Factors of 4 will be 2 and 2. I also have a squared, so I'm going to take 2 and divide by 2, which will give me 1. So as I'm simplifying this, this becomes 2a on the square root of 5. Now I want to make sure that I simplify the 45. Notice there are no a's on the inside, so I just need to simplify the number 45, which will give me, now subtracting, you had an a on the outside, 3a on the square root of 5. As we get to this step, we can see that we have two values that are the same. So 2a minus 3a is just a negative a. That's going to be on the square root of 5. Now we're going to transition into multiplying radicals. So all we have to remember is to have two radicals and then multiplying and taking the two numbers inside the radicand, multiplying them together, and then I'm going to simplify. So if I have the square root of 3 times the square root of 5, that's going to equal the square root of 15. Now if I were to break down 15 to try and simplify, the only two factors are 3 and 5, so there's no pairs. Therefore, we leave it square root of 15. As I look at some of the other examples, though, notice that I could factor out perfect squares. Now you have two options when doing these, and I'll do alternating versions every time. I could go through and simply multiply the two numbers inside of the radical. And if I do so, I have 5 times 10, which gives me the square root of 50. And then I can come in and break down 50, get 25 and 2, 5 and 5. So my final answer when I multiply the square root of 5 times the square root of 10 would be pair of 5, so 5 on the square root of 2, because the 2 is left over. The other way of doing this is you can break these down before you multiply. So I can say square root of 12 is really the square root of 4 times the square root of 3. And that the square root of 6 is the square root of 3 times the square root of 2. And then I want to simplify if at all possible. Well, I know the square root of 4 is 2. I notice I have a pair of square root of 3's. And I'm left with a square root of 2. So on my outside, I have 2. And then if I multiply these, that would give me 3. Square root of 2. So 2 times 3 is 6. My final answer, 6 on the square root of 2. It is completely up to you and whatever version you prefer to do. Personally, I like to just multiply and simplify the end. Seems to be easier for me, but you do not have to do problems the exact same way that I do. So here I have 10x times 2x, which will give me the square root of 20x squared. So this step I would just come in and break down 20 to be 4 and 5, and break down 4 to be 2 and 2. Then I would take my x squared, take the exponent of 2, divide by 2, because I'm putting it in pairs, where I get 1. So I have 2 and 1x on the outside, and then a lonely 5 left on the inside. As I work through number 12, 6 times 3 would be 18. And I can break down 18 to be 9 and 2, and 9 to be 3 and 3. So I'll have a pair of 3's, so 3 on the outside, with a 2 left over on the inside. Number 13, as I multiply these two, 3 times 18 gives me 54. And I can break down 54. 9 times 6. 9 will be 3 and 3. 6 is 2 and 3. I have a pair of 3's and a 2 and a 3 left over. So 3 goes on the outside, and then 2 times 3, which will be 6, goes on the inside. Don't let the fact that there's a variable throw you off. Still going to multiply, so 8 times 3 gives me 24, and then a times a gives me a squared. 24 I can break down to 2 and 12. 12 to be 4 and 3, and 4 to be 2 and 2. So a pair of 2's with a 2 and a 3 left over. And then when I deal with a squared, that's 2 divided by 2 gives me 1. So as I write my final answer, I have 2 times 1a on the radical of 2 times 3, which is 6. Now the things that are different about number 15, if you notice, I have numbers on the outside of my radicals. So I still want to start by multiplying those two things. So 3 times 5, which is going to give me 15. And then I multiply my inside. So on the inside will be 3 times 7, which will be 21. Well, the only factors of 21 are 3 and 7. So in this case, I am in simplest form. For number 16, 5 times 2 on the outside, which gives me 10. And on the inside, 7 times 14, which will give me the square root of 98. Now, I need to break this down. And when I do that, 98, you can break down to 7 and 14 again. So factors 7 and 2. I have a pair of 7's. So on the outside will be 10 times 7. While the inside will be square root of 2. Then I can just simplify that to give me 10 times 7 is 70 on the square root of 2. As I get ready to solve the last one, there's a number on the outside, so 3 on the square root of 75x squared. Simply break down 75 to be 25 times 3, 5 times 5. Take x squared, I do 2 divided by 2, which equals 1. So on the outside I have 3 times 5 on the inside. Oh, and I have an x as well.